Okay, in this video I'm going to go over several examples of one-way ANOVA and factorial ANOVA based on this data set that we have here on 30 with 30 cases. So these cases, each row represents an individual protocol, and so each person's response or each person's value on each variable is noted. So person 1, that person's a male in treatment group 1 or a CBT group, and that's their score on anxiety after the treatment period. So basically we have, as you can see, we have three variables. Gender and treatment are basically going to be independent variables in our subsequent analyses. Anxiety will be our dependent variable. Gender is coded 1 for male and 2 for female. And treatment group is coded 1 for cognitive behavioral, 2 for behavioral group, and 3 for a waitlist control condition. So basically what's happening is that your counseling researchers studying the effectiveness of different counseling interventions on clients' level of anxiety. You unfortunately you don't randomly assign the clients to the three different groups. So you have basically 11 clients that are in a CBT condition, 10 in a behavioral only condition, and 9 in a waitlist control condition. And like I said, the codings are 1 for treatment, 1s are for CBT, 2 is for behavioral only, 3 is for waitlist control. For gender, 1 is for male, 2 is for female. So these two variables are nominal, and anxiety is an interval scaled variable. So this is reflecting their level of anxiety following the treatment period. So looking at the data set in SPSS, you can see right here you have the little icons for nominal and scale variables. This is because this screen right here, this is reflecting an updated version of SPSS where you get the scaling of the variables that are noted. So first, we're going to perform a one-way ANOVA comparing the three treatment groups on anxiety. We're going to ask for statistical significance, effect size, and power. And we're going to ask for the homogeneity of variance test to test the homogeneity of variance assumption. And then we are also going to just kind of move on to activity 2 here and report on Tukey's post hoc test. So we're going to ask for Tukey's post hoc test in addition. So what we'll do is we'll go to Analyze, we'll go to General Linear Model, Univariate, we'll put Anxiety in the Dependent box, we'll put Treatment in the Fixed Factors box, we'll ask for Plots, we'll move Treatment over to the horizontal axis, click on Add, Continue, Post Hocs, we'll click on Treatment, move it over to the Post Hocs test, and then click on Tukey's. We'll click on Continue here. Now to get effect size and power, we have to go under Options. We'll move these over to the Display Means box. We'll ask for descriptives, effect size, and power, and homogeneity tests in order to get Levine's test. So we'll click on Continue, and then on OK. And so now you can see our output. You'll notice that we have our descriptive statistics here with our three groups noted. These are the means of the three groups. So descriptively, anxiety levels following the quote-unquote intervention period was highest in the waitlist control group. It was lowest in the CBT and the behavioral only groups. And then before we interpret the ANOVA and try to make sense out of that, we also want to look at some assumptions related to the analysis. Because for a valid interpretation of the analysis of variance, we want to make sure that our data are meeting those assumptions. Otherwise, it can call our ANOVA results into question. So one assumption, a key assumption, is homogeneity of variances, and that is assessed in SPSS by using the Levine's test. So basically, you have a significance test associated with this. So essentially it's like this, that basically what we're doing is we're comparing the variances of the three groups on our variable, and trying to determine if they are equal or if they are different. If the variances are significantly different, then that actually would suggest a violation of the assumption, which would not be a good thing when interpreting the one-way ANOVA results. Um, so conventionally, when it comes to testing mean differences, we kind of are shooting for there to be statistical significance. When it comes to testing assumptions, such as homogeneity of variances, we generally are not wanting there to be statistical significance. So we can compare this p-value here against a conventional alpha level of 0.05 and determine if this test is statistically significant. And so you can see that really we're right on the cusp of statistical significance, which raises some question about whether or not our assumption is met. Basically, our p-value of 0.052 is slightly greater than 0.05, but not much. So there is some question about whether or not we have violated that assumption. Nevertheless, we'll keep that in mind as a potential limitation when we start interpreting the ANOVA test results. So going through this route here, you can see we have our independent variable name, treatment, we have our degrees of freedom between, as well as our F value and the p-value that's printed out, which is 0.000. Keep in mind that SPSS by default rounds off to 3 decimal places. So technically the p-value is not 0. It's actually going to be less than 0.001. So conventionally, when you're writing this up, you would use p less than 0.001 when interpreting when writing up the p-value in a published report. The effect size is the partial eta squared value that we see right here, which is 0.634. You can see that if we use Cohen standards for small, medium, and large effect, for eta squared values around 0.01 would be considered small, around 0.06 would be considered medium, and around 0.14 or greater would be considered a large effect. So this is clearly a large effect, meaning that there are large mean differences on anxiety across the groups. The power that you see right here, this is just the probability of correctly rejecting a false null hypothesis. You can see it's 1. So you can't get any higher than 1, and you can't get any lower than 0. So conventionally, you're shooting for a power level at 0.80 or above. But this is sort of computed post hoc after the analysis, after you've collected your data and run your analysis. So I don't find it terribly useful because you'll note right away whether or not you were able to reject the null. So I just don't really find it terribly useful, but that's what this is. It's basically the probability of correctly rejecting a false null hypothesis. So when we scroll down a little bit, just clear that out. I'll scroll down. We can see our 2 keys post hoc tests. So you've got the CBT group being compared to the behavioral only group. So you can see, basically think about it as the mean for group I minus the mean for group J. So in effect, if we take the mean for CBT, which is 4.727, subtract 6.1, which is the mean for the behavioral group, you get negative 1.3727. So that negative value means that the CBT group has a mean that's 1.37 points lower than the behavioral group. Now, is that difference statistically significant? We look in the significance column here at the p-values. You can see a p-value is greater than 0.05. So we would say that that difference between these two groups is not significant. When we look at the comparing CBT versus the waitlist control group, you can see that the CBT person scored on average 7.7 points lower than the waitlist control group. And you can see that that difference was statistically significant. When we compare the behavioral group versus the waitlist control group, you can see that the behavioral participants scored 6.3 points lower on average than the weightless control group, and you can see that that difference was significant. So, and then basically down here you have a replay of the same test that we just covered above. So you can see that really two of the three comparisons were statistically significant. Now, let's go back and we'll look at the next activity. So we're going to rerun the ANOVA and request a planned contrast comparing persons who received CBT or behavioral-only therapies against those in the waitlist control condition in terms of anxiety. So in this case, we're asking for essentially a complex contrast. And this will require the use of syntax. So here's an example of the syntax that will be generated. And so we have to use contrast codes in order to make that comparison. So to do that, we'll go into Analyze, General Linear Model, Univariate, and I'll go and click off Post Hoc. I'll just click this off altogether because we're just going to do the planned contrast. And so everything else is exactly the same. Now we just need to get to a syntax file so that we can modify the syntax in order to carry out the contrast. The reason why I'm doing this in a separate step is because just to keep it logically consistent with how you would typically approach the use of contrast versus post hoc tests. Post hoc tests are utilized in exploratory fashion, and you generally use planned contrast when you are testing some type of a priori hypothesis. So it really involves a more confirmatory mindset. From that standpoint. So you generally will carry out either a post hoc test or a planned contrast. Probably most of the time when I'm reading the research literature, people will just carry out Tukey's post hoc tests or something of that nature. But sometimes people will choose planned contrast, but you don't generally do both of them. So for that reason, I've clicked off of post hoc, removed all of our previous selections. And so I'm just leaving plots the way they are. I'm leaving options the way they were. And now I'll click on paste. And so this is the syntax for this analysis. And so what I have to do in order to carry out this analysis, keep in mind that the use of contrast codes, essentially what they're utilized for is to assign weighted means for the comparison. So let's say I want to compare the mean for group 1 versus the mean for group 3. What that would mean is that I will have, I'll have my sample mean for group 1, the sample mean for group 2, and sample mean for group 3. And essentially, I want to make a comparison. So if I want to compare groups 1 versus 3, all I have to do is multiply. I can multiply 1 times the mean for group 1, which would be the mean for group 1, 0 times the mean for group 2. So that effectively makes this 0. And then I will make the contrast code for group 3 a -1. And so then that reduces to the mean for group 1 minus the mean for group 3. Okay, so basically we have to use contrast codes in order to specify the comparison that we want to carry out. So this is an example of a simple contrast comparing two means, and we want to keep in mind that the contrast codes must sum to 0. Now for this particular contrast in this example, we're going to take the average of groups 1 and 2 and compare the average mean of 1 and 2 versus the mean for group 3. So in terms of using contrast codes, we'll lay it out this way. We can say there's group 1, group 2, and group 3 right here. Oop. Now for the contrast codes, we can use to get the average of 1 and 2, we can just multiply by 0.5 for groups 1 and 2. Or if we wanted to, we could type in SPSS, we could use 1/2 and do the same thing. And then for group 3, we would use a -1 right here. So that effectively reduces to the mean for group 1 plus the mean for group 2 divided by 2, and then minus the mean for group 3, which is what we have right here. So this is a -1, by the way. So that's how we're going to lay this out. So this is an example of a complex contrast because it involves more than two group means. So we'll clear this out and we'll use our syntax here. So I've got to get rid of this little period, and I'm going to use the L matrix command. I'm going to move this over and just say \L matrix, and typically I like to give it a title because that appears underneath the output. And so I'm just going to call this, let's see what I included in my previous example here. Now, I guess I didn't include a name or a title, but I'll go ahead and do that anyway. So I'll say average of 1 and 2 versus 3. So just designating my groups. Then I'm just going to type in treat for, and that is the name of my independent variable. So keep in mind, you have to have the exact name of the independent variable that's listed up here. You know, in terms of our syntax, when we click the paste command, it generated all of our options, and all we're doing is making a slight modification. But the univariate ANOVA command right here is followed by the name of the dependent variable by, and then the name of the independent variable. So we got treat, and I can use 0.5, 0.5, and -1, whoops, -1 as my contrast codes. I'll press period here and highlight everything and click the green button and run. So you'll notice that it's generated all the same output as before, but in this case we have our hypothesis test for the planned contrast. So you can see right here we've got, there's our mean difference. So that's basically if I take the average of the means for groups 1 and 2 and subtract the mean for group 3, that's the difference between those for that comparison. Down here you've got the significance level, that's the p-value that is listed. Again, it's rounded off to 3 decimal places, but if you're reporting this in a research report, you'd say p less than 0.001. You also have a confidence interval as well, and if you wanted an interval estimate around the contrast estimate. So at this point, let's see if there's anything else I wanted to mention. So looking at our output, you can see Levine's test indicated a near significant difference in the variances on the DV. So you know, we have to kind of consider that issue when we are looking at interpreting the ANOVA results. Nevertheless, if we just interpret the ANOVA results by themselves, there's evidence of significant mean differences on the dependent variable. And the effect size would be large, and the power of the test would be large as well. We also see that Tukey's post hoc test revealed significant mean differences between CBT and the waitlist control, and the behavioral group and the waitlist control, but there was no difference between the CBT and the behavioral groups. When we look at the contrast results, you can see that that there was a significant difference between the average of the means for CBT and behavioral groups as opposed to the waitlist control group. So at this point, and keep in mind too that the planned contrast, we just said request a planned contrast. So at this point, you know, it's largely going to be a non-directional hypothesis that's being tested out concerning the comparison. But keep in mind that you can run directional hypotheses using SPSS as well. It just involves, when you're looking at your p-value, if you're testing a directional hypothesis, be dividing that p-value in half to get a correct p-value for a one-tailed test. But we didn't do that here. Okay, so activity 4, we're going to run a 3x2 factorial ANOVA. We're going to ask for main and interaction effects, including statistical significance, effect size, and power. And also ask about homogeneity variance assumption because that's a requirement. And then we're also going to ask for down here. So I'm going to go ahead and kind of take care of 4 and 5 all together, rather than running them separately, because we can easily accomplish this in one swoop. So I'm going to go to Analyze, go down to General Linear Model, Univariate. Okay, so in this case we're running a factorial ANOVA. So we're going to include gender as a second fixed factor. We're going to leave anxiety where it is. Treatment and gender are my independent variables. In terms of plots, I'm going to ask for a profile plot of the interaction. I'm going to go ahead and I'll go ahead and ask for a profile plot of gender, and then but mainly I'm asking for a plot of the treatment by gender interaction. So I'm going to put treatment on the horizontal axis and gender on the separate lines. It's really arbitrary how you do this. It doesn't make a difference. I typically put sort of my focal independent variable on the horizontal axis and then my moderator variable on the separate lines, just because it's easier for me to kind of conceptualize. So once I've done that, I'll click on Add. And so that, when I say that, what I mean by that is that I'm sort of mainly interested in the effects of treatment on anxiety, but I also wanted to kind of visualize how the differences appear by gender group. So that's the logic there. So I'm going to click on Continue. I could still theoretically ask for Tukey's post hoc tests for the treatments if I wanted to do that. It wouldn't make any sense to ask for gender because there's only 2 groups for that variable, and you'll get a little bit of an error message in SPSS. It's not going to blow up or anything. It's just it's just basically saying, hey, you can't run a post hoc test when you only have an independent variable with 2 levels. So I'm going to leave that off. And really, to tell you the truth, in this activity example right here, I don't even ask for Tukey, so I'm just going to leave that off as well, because it's not really necessary. Under Options, now I want to select the whole bunch of these effects and interactions. I'm going to move them over to the Display Means box. Keep descriptives, effect size, power, homogeneity tests, all those as they were, and I'll click on Continue. Now, so that right there, if I just stop there, I'm essentially going to be carrying out activity 4, which is running a 3x2 factorial ANOVA. And I'll just go and show you now, if I go ahead and do that, what it looks like. You can see, in terms of the output, you can see we've got our means for the CBT, behavioral, and waitlist control groups by gender. So you can see there's the males in CBT group, females in the CBT group, males in the behavioral group, females in the behavioral group. In the waitlist control, males were higher than females following treatment or following the intervention period. So that's what that is. So that's kind of capturing really the cells that would be associated with the interaction. With respect to the mean on CBT across levels of gender, it's 4.7273. The mean for the behavioral group is 6.1. That's across levels of gender. And then the waitlist control group is 12.44. So that's across gender as well. If I want to look at just gender differences across levels of the treatment groups, you can see that the male mean on anxiety was 6.3, females was 8.667. When we look at Levine's tests, our assumptions concerning the ANOVA results still are in play. We still have the assumption pertaining to homogeneity of variances. And so again, we are looking for the p-value to be greater than 0.05 for the Levine's test. And so in this case, it clearly is. And so in other words, that would indicate to us that that would provide good support that we have maintained, that we have met our assumption concerning the ANOVAs. Now, when we look at the test of between subjects effects, you can see we have a main effect of treatment, main effect of gender, and then we also have the treatment by gender interaction. So here you can see that we essentially the test of the main effect of treatment, which basically involves, if I kind of scroll up just a bit here, when we're testing the main effect of treatment, we're looking at whether this mean for the behavioral group and this mean are significantly different from each other. So that's referring to a main effect of treatment, because we're looking at these means and we're not considering the role of gender or anything like that. So in this case, you can see that the main effect of treatment was statistically significant. All right, so you can see that the effect size using Cohen standards was indicating a large effect, which is 0.782, clearly greater than 0.14, which is the conventional threshold for a large effect. Power was obviously high as well. So when we look next at the gender main effect, you can see in this case we're comparing males versus females, and we see that that was statistically significant, and we also have a large effect size as well. Power was lower, but like I said, really this is more descriptive. It doesn't really tell you a whole lot in and of itself. And we already know that we were able to reject the null, so obviously it was powerful enough to be able to reject the null. So in this case right here, we have a significant gender main effect. Then when we look at the interaction effect, that's where we are comparing these cells right here. So we're looking at the means for the behavioral CBT and weightless control groups by gender. So in this case, you can see that the interaction effect was statistically significant. The effect size was large, as was the power of the test. So if we want to kind of visualize the interaction, we can scroll down, go to our profile plot. So this is a profile plot of the main effect of treatment, profile plot of the main effect of gender identification, and then a profile plot of the interaction. So you can see if our interaction, if there was no interaction, we would expect the plot of means for the two groups, for the two gender ID groups, to be more parallel. And so in this case, it's clearly not. So you can see that the difference between male and female in the CBT group was small here. It actually gets larger in the behavioral group. So the behavioral group, there's a lot more differential effect there. And then the weightless control group, there was a small difference here. You actually had males being a little bit higher than females in this particular condition. So the lines are not particularly parallel. It looks like that there's not really much of a difference here, not much of a difference here, but that there's a bigger difference between males and females in the behavioral behavioral group. So the problem with profile plots is that you know, they don't really allow us to test for differences between groups across levels of the moderator. Our moderator variable is gender identification, which is what we have right here. So let's say we wanted to test for statistical significance for these comparisons right here. And well, we can do that using simple effects tests. And so the way that we can accomplish that in SPSS, you'll notice in my little PowerPoint here that we're going to use the paste syntax command. We're going to use the compare commands, and we're going to ask for Bonferroni adjusted simple effects tests as well. So pertaining to that, what we will I'll show you what it would look like. So if we ask for to get simple effects tests, we have to generate all of our syntax as before. We then basically, you'll see that in line 10 right here, it's got tables, treatment by interaction, or treat by gender interaction. So we're adding a compare command and Bonferroni adjustment command as well. So to do this in SPSS, we'll go to Analyze. We'll go back to where we were before. Everything will leave exactly the same, but in this case, we'll also click on Paste. Syntax file opens up. So here's the new syntax, and you can see now it's got univariate ANOVA anxiety, which is my dependent variable, by treat, which is the name of the independent variable for the treatment group, and gender, which is my gender identification variable. So those are my two independent variables here. You can see down here that we've got tables treat by gender. So it's on this line that I'm going to add a compare command. So I'll type in compare, and then if I want to compare the means, if I'm using gender as my moderator, and I want to compare the treatment groups, or within each treatment group, compare males and females, then I'm going to type in gender to foster that comparison. That's the name of the moderator variable that I'm using. And so within the CBT group, I'm going to compare males and females. Within the behavioral only group, I'm going to compare males and females. And within the wait list control group, I'm going to compare males and females. I'm also going to add in ADJ and then type in Bonferroni. And that just means that it's going to give me Bonferroni adjusted simple effects tests, because there's basically going to be three of them. And so let's say I want to adjust the 0.05 level for the multiple comparisons that are being carried out. So now I'm going to highlight all of this, click on Utilities here and the green arrow, and then scroll down. You can see everything is exactly the same as before, but now you can see that we have our simple effects test listed under pairwise comparisons. You can see that for the CBT condition, the comparison between males and females, there's the mean difference. So basically males were scoring 1.2 points lower on average than females in the CBT condition. And you can see that that difference was not statistically significant. In the behavioral only condition, you can see compare males and females. The males scored 5.8 points lower on average than females, and that difference was statistically significant. When we look at the waitlist control group, when we compare males versus females, males were actually higher by about 1.9 points on average, and that difference was not statistically significant. So you'll notice that the next lines right here are just basically a rehash of the tests that you see on the first of those rows. So putting this all together then, if we scroll down a bit and look at our profile plot, that basically is telling us that this comparison right here, that was non-significant difference. Here you can see that this difference was non-significant, and right here you can see that this difference was statistically significant. So that's basically consistent with an interaction that's taking place. The lines are clearly not parallel. So at any rate, the simple effects tests are pretty useful for exploring aspects of the interaction. They're not necessarily great for always identifying an interaction, but they are useful for sort of exploring patterns within the interaction effect. So that basically ends our discussion of illustrating the one-way ANOVA and the factorial ANOVA using this data set. I will quickly kind of point out too that if we wanted to go back and let's say just to the one-way ANOVA for a second, and let's say I wanted to run the one-way ANOVA and ask for Tukey's post hoc and the plan comparisons using sort of the simpler route in SPSS, you could easily do that if you just go to Analyze, Compare Means, One-Way ANOVA. This is really kind of a crummy way of doing it, mainly because if you're running factorial ANOVA or whatever, you might as well get used or running more complex ANOVA designs like ANCOVA, then you might as well get used to running the general linear model and using the univariate option. But if you just wanted to run like a quick one-way ANOVA with those specifications, you can do that just going to one-way ANOVA. We were running treatment as the factor, that's our independent variable. Anxiety as the dependent variable. If I click on options, I can ask for descriptives, means plot, homogeneity tests. If I want to ask for Tukey's post hoc tests, I can ask for Tukey's right here. If I want to ask for contrast, like perform that plan contrast I showed you earlier where we were comparing the average treatment groups 1 and 2 versus the mean for the group 3, the wait list control. You would just use a little contrast box right here. You just say, 0.5, add that would be for group 1. This would be for group 2, and then this would be for group 3 right here. Click on add. See the coefficient total has to sum to 0. Just click on continue and on OK, and here you go. So in this case right here, you can see there are the means that we saw before, standard deviations, etc. There's Levine's test that we saw earlier. Here's the ANOVA F-test and significance level. But again, you don't get power and effect size by going through this route, so it's not terribly handy in many respects. The contrast coefficients just lay out the actual comparison that was made. You have contrast tests. This is the mean difference, or the difference between the average of the means for groups 1 and 2 versus group 3, which was the waitlist control group. So that's exactly the same as before. And here's our p-value that's listed. I just went and ran Tukey's alongside everything as well, and so you can see that we have the same Tukey's post hoc test results as we saw previously. And this was the profile plot of the means. So that pretty well concludes this illustration of one-way ANOVA and factorial ANOVA.